Alright, the second type of colligative property we're going to talk about is boiling point elevation. So when we add solute to a solvent to make a solution, the boiling point of our new solution is higher than the boiling point of the solvent by itself. And this is directly tied to our vapor pressure idea. Since our solution makes less vapor, it requires more energy to create the same amount of vapor that we would have in the external pressure, therefore creating a larger boiling point. So we can see that here in the phase diagram. The pink line represents our solvent by itself. The blue line or purple line represents the solution. Since we have less vapor pressure in the solution compared to the solvent, it shifts the curve to the right and requires more energy to make sufficient vapor to reach the adequate external pressure amount. So we have a delta T, or a change in temperature from the solvent by itself to the solution. And the solution is always going to have a higher value. The third colligative property is freezing point depression. So I'm going to give you the concepts for boiling point and freezing point first, and then we'll do the math, because their equations are very similar. So freezing point depression has the same idea, adding solute to our solution, to our solvent, creating a solution, also causes a shift in the phase diagram. For freezing point, we're looking at this melting freezing line over here. So here is the pink line representing solvent by itself, and then we have our purple line representing the solution. So we can see it shift to the left or go the other way, so our freezing point decreases compared to solvent by itself. And the reason this occurs is because we have solute molecules mixed with our solvent molecules. And remember, in order to freeze something, the molecules have to get close together and arrange in a lattice formation. If there are solute molecules in the way, this prevents the lattice formation as easily, and we have to remove even more energy in order to create that lattice. Alright, so our freezing point is always going to be lower in the solution compared to the solvents alone. We have to decrease the kinetic energy even more. So this little picture kind of summarizes it for you. Having the solute molecules around the solvent molecules causes a lowering of the freezing point. So your friends keep you from freezing. The more solute molecules you have, then the lower the freezing point is going to be. The colder it has to get before you can freeze. Alright, so let's look at the math for each of these. So for boiling point elevation and for freezing point depression, the equations look very similar. We're looking at the change in the temperature from the solvent alone to the solution is proportional to the molality. Okay, so this funny M here is molality. This is our concentration unit, which is moles of solute per kilogram of solvent. Alright, so remember these concentration units. It's a little different from molarity. It's not mole fraction. So for freezing point and boiling point equations, we're going to look at molality. So freezing point looks very much the same, looking for the change in temperature proportional to the molality again. Now these K values that we have here are the proportionality constants. So these constant values depend on the solvent, not the solute. So it depends on what you're making your solution out of. And these values will usually be given in the equation. There's something you can look up online as well. So they are for the solvent. So they are labeled Kb for a boiling point solvent constant, or Kf for the freezing point constant. Now our delta T's represent the difference between the boiling point or freezing point of the solvent by itself and the new solution that we're making. But these should always be positive values. Your change in temperature should be a positive value regardless of whether we're talking about boiling point or freezing point. So our delta T of boiling is solution minus solvent. Our delta T of freezing is solvent minus solution. Okay, and there's an easy way to remember this, and when we do the math, I'll show you what it is. Alright, so let's look at our first example. What is the boiling point of the solution when 8.79 grams of lactic acid dissolved in 30 grams of water? And then second question, what is the freezing point? Alright, so we're looking for the temperature at which our new solution is boiling and then freezing. And we have our constants given here, our K values, both of them are for water because that's our solvent. So we'll do the boiling temperature first. So change in boiling temperature is equal to Kb times molality. Now since Kb is given for us, we just need to find the molality. So molality is moles of solute over kilograms of solvent. So up here we already know we have 30 grams of water. This is our solvent. So we're just going to move the decimal over to convert this to kilograms. Our solute is going to be the lactic acid, and we need to turn our grams into moles. Alright, so 8.79 grams. If I want moles, I'm going to divide by molar mass, and that's given for us for lactic acid. 90.08 grams per mole. Alright, 8.79 divided by 90.08. So 0.097558. Alright, so these are going to be our moles for our solute. So over here, our change in temperature for boiling point equals our Kb value, 0.51, times our molality, so you put moles on the top, over kilograms of solvent on the bottom. Alright, so then we just have to multiply. Alright, moles divided by kilograms, that gives us our molality, 3.25. And then we multiply by our Kb value to get our change in boiling point, 1.66 degrees Celsius. Now since this is a change in boiling point, if I want to know the actual boiling point, I need the boiling point of our solvent, which is water. So water boils at 100 degrees Celsius. And boiling point elevation means our temperature goes up, so I'm going to add the 1.66 is 101.66 degrees Celsius. So instead of remembering delta T is something minus something else, we just remember boiling point of solvent plus whatever the change is, because boiling point has to go up. Alright, we can also do our freezing point. So similar equation, using our Kf, but using the same molality again. Since we already calculated molality before, we're not going to recalculate it, it's the same value. We're just going to insert it with our Kf. So our molality was 3.25. We're going to multiply by the Kf. So 3.25 times our Kf value gives us 6.045 degrees Celsius. And remember, this is also a change. So this is a change for our freezing point. Freezing point depression indicates that the freezing point goes down. So we're going to take the freezing point of water, which is 0, and we're going to subtract our change, because freezing point has to decrease. So our new freezing point is negative 6.045 degrees Celsius. Alright, so simple enough. We can also use boiling point and freezing point to try to identify a solute. Alright, so the next example we're going to look at, we're going to try to identify the solute based on molar mass. So using the equations that we just talked about for our delta T's incorporating molality, we can rearrange the equations using molar mass multiplied on each side to turn our moles of solute into grams. So frequently if we have a solution, we're going to be able to weigh out grams, mix it in with our solvent to create a solution, and then measure freezing point or boiling point. Even if we don't know what our solute is, we can measure it in grams. But we're not going to know how many moles we have if we don't know what the solute is. So we need our equation rearranged, incorporating grams that we can weigh out of both the solute and the solvent. So here's our rearranged equation. Molar mass of the solute is equal to our Kf, again, our constant value, times the mass of solute, and this is going to be in grams, divided by the delta Tf. Okay, delta Tf is what we had up here, times kilograms of solvent. So we're going to use this equation for the next example. Alright, we have a solution of 0.5 grams of adrenaline. That's going to be our solute, in 18 grams of CCl4, which is going to be our solvent. And we know this solution has a boiling point of 77.3 degrees Celsius. We're going to use that information to find the molar mass of adrenaline. So based on our equation up here, we're going to fill in our mass. Our Kf is given for us. We have some constant values down here. And our delta T. Alright, so let's plug in what we have. We're looking for molar mass. We have Kf times mass of solute over delta Tf times kilograms of solvent. Alright, so here's our equation. Now our Kf is given for us. Well, we have boiling point information, so let's make this Kb instead of Kf. Delta Tb, that'll be easier. And then we'll go back to our freezing point. So we're going to work with boiling point information. So that's our Kb. Alright, so Kb is 5.02 times the mass of our solute, which was given at 0.5 grams of adrenaline, divided by kilograms, 0.018 kilograms of our solvent. So I'm just moving the decimal place over. And then the last thing we want to put in here is our delta T, our change in boiling temperature. So our solution was 77.3 for boiling temperature, but solvent by itself, all right, was 76.54. So in order to find the change, we're going to subtract. And remember, delta T needs to be positive. Alright, so let's do our math. 5.02 times 0.5 divided by, okay, here's where we're finding our delta T, and then divided by our kilograms. So 183.5 grams per mole. Alright, so this is our molar mass for our solute, which is adrenaline. Just using our grams of solute, kilograms of solvent, and using our delta T. Alright, question B asks for the freezing point. Now there are two ways we can do this. We can either use the boiling point, we can either use the molar mass information that we had before and incorporate that into finding our freezing point information, or we can go back and find the moles for molality. So I'm going to do this both ways so we can get an idea. Alright, the first way I'm going to do this is by using the molar mass that we have. So I have 183.5 grams per mole that I just found for my molar mass. I'm then going to use the Kf value, 29.8, the grams, 0.5 grams, over. Here's where I don't know the change in freezing point because I don't have that data, but I do know kilograms of my solvent. So in this case, now that I know the molar mass, I can solve for delta T. So we're going to multiply delta T and our kilograms onto this side. So we have 183.5 times 0.018, 3.303. Alright, equals, then I'm going to multiply the 29.8 times 0.5, 14.9. Then we can divide both sides to isolate the delta T. Alright, so 14.9 divided by 3.303, 4.511. Alright, so this is our change in freezing point. And remember, since it's the change, we want to know what the freezing point's going to be. We're going to go back to our original freezing point from our solute, or solvent. So freezing and melting are the same thing. So we have negative 22.3, negative 22.3, and remember we're going to subtract the change because our freezing point has to go down. So negative 22.3 minus our change gives us negative 26.8 degrees Celsius for our new freezing point. Alright, so that's the idea of using the equations in order to identify an unknown or to find a new freezing or boiling point. The other thing to remember when we're looking at these types of equations is to look for electrolyte solutions. So with vapor pressure, boiling point, freezing point, and osmotic pressure, we can either have a non-electrolyte solute or an electrolyte solute. So we need to know what kind we're looking at and then being able to incorporate the I value. So for freezing and boiling point, if we have an electrolyte solution, so I is not 1 anymore, we just need to multiply by the I value. So for example, what is the freezing point of 1.5 Molal aqueous solution of magnesium sulfate? Alright, so our delta T for freezing, we have Kf times molality times I, because electrolyte solution, I is not 1. In this case, I is going to roughly be 2. We have 1 magnesium and 1 sulfate ion. Remember, they stay together. The SO4 stays together as a polyatomic. So filling in our information, we have Kf, which is 1.86. I'm getting that from up here. We have our constant values. All right, times our molality of 1.5, that's given for us, times an I value of approximately 2. All right, 1.86 times our 1.5 times 2. 5.58 for our change in freezing point. And since the freezing point of the solvent alone is 0, our new freezing point is 0 minus the change, so negative 5.58 degrees Celsius. Alright, the second one, 3 molal aqueous solution of sucrose. If we look at the formula for sucrose, this is a covalent compound, pretty large one, but it's not going to ionize. It's not an electrolyte solution. This is a non-electrolyte solution. And we want to know the boiling point. Since it's a non-electrolyte solution, that means I is going to be 1 for sucrose. So we can kind of ignore the I value. So delta T, in this case boiling, keep wanting to do freezing. In this case boiling equals our KB value, 0.512, again I'm getting that from up here, times our molal, 3 molal, and our I value would be 1, so you can put it or not put it. Just make sure you know whether you have an electrolyte or non-electrolyte solution. Alright, 0.51, 2 times 3 times 1 is 1.536 degrees Celsius. So this is our change. If we want to know what the new boiling point is, we take the boiling point of water, which is 100, and we're going to add our 1.536. So 101.536 degrees Celsius. Alright, so make sure you can identify electrolyte solution versus non-electrolyte solution. Okay, we're going to do one more example with an electrolyte solution so we can see how we can incorporate this. So 18.75 grams of magnesium chloride added to 150 mils of water at 35 degrees Celsius. We want to find both the boiling point and the freezing point of the solution that we make. So we have the density of the water at our temperature so that we can be sure to get moles or in kilograms. And we have our 2 kBkF values for the solvent, which is water. Alright, so we'll do boiling point first. We have magnesium chloride, which is an electrolyte solution. So our I should be approximately 3, because we have 1 magnesium, 2 chlorine. Alright, and then we have our Kb value, and we need to find our molality. Alright, since we have our constants and we know our I, let's focus on molality. This is going to be moles of solute over kilograms of solvent. Alright, so we are given 18.75 grams of solute, so we just need to turn this into moles using our molar mass. So 18.75 grams magnesium chloride. We're going to divide by molar mass. So if we look at our molar mass here, we have 24.3 for magnesium plus 71 for the two chlorines, so approximately 95.3 grams per mole. So our 18.75 divided by our value gives us 0.1967 moles. Alright, then define molality. We're going to put that over our kilograms. So 0.1967 moles. Let's find our kilograms, because for our water we were given 150 mils. So 150 mils. We're going to use our density value to turn that into grams. Then we can turn the grams into kilograms. So we're going to multiply by our density. Cancels out our volume. And then we're going to turn the grams into kilograms. Alright, so 150 times 0.994 divided by 1,000. So 0.1491 kilograms. Alright, so we have our moles, we have our kilograms. So now we're just going to do our ratio. 0.1967 divided by 0.1491 gives us 1.3 for our molality. Alright, so then we can plug that in over here. So we're looking for change in boiling point. We have Kb given for us. We now have molality, and our I value should be approximately 3. So now when we multiply, we get our change in boiling temperature of 2.02 degrees Celsius. Since water is our solvent, we're going to add that to our 100 to get 102.02 degrees Celsius for our boiling point. For our freezing point, we're going to incorporate the 1.86 for our Kf. Our molality stays the same, 1.3, and our I value stays the same. Alright, 1.86 times 1.3 times 3 gives us 7.254 for our change in freezing point. And we're going to subtract that from the freezing point of water. So 0 minus 7.254 gives me negative 7.254 degrees Celsius. Alright, the last thing we're going to talk about with this has to do with ranking solutions based on this change in boiling or freezing point. So there's two factors that determine how much of a change in freezing or boiling point you're going to see with a solution. Obviously, the concentration is a big factor. The more concentrated the solution, the bigger the change you're going to see in freezing or boiling point. The second factor that's important is going to be that Van 't Hoff factor, or the I value. The larger the I value, the larger the effect you're going to see. So when we're ranking solutions, we need to pay attention to both quantities, the concentration and the I value. So I'm going to make a table that allows us to look at each of these values. And we're going to multiply the molality times the I value to come up with what I call a factor. And the factor determines how big an effect we're going to see. So in this case, we're looking at freezing points. Alright, so we're going to rank these based on freezing point. The larger the factor, the lower the freezing point is going to be. Alright, so I'm going to write that over here. The larger the factor, the lower the freezing point. Alright, so once we get our table filled out, we're going to look at this relationship. So let's see what we have first. We have KCl, that is a 0.25 molar, a Molal solution. KCl has an I value of approximately 2. So when we multiply 2 times 0.25, the factor becomes 0.5. Alright, our next one, NCl3. Molal is 0.015. NCl is a covalent compound, not an ionic one, so it's not going to ionize, so I value is 1. So it's just 0.015. Alright, our third one, iron nitrate. And we have a molality of 0.010 and an I factor of 4. 3 nitrates and 1 iron. So when we multiply here, we get 0.040 for our factor. Alright, our fourth one is methanol. Our molality was 0.05. And our I value again is going to be 1 because this is covalent, it's not going to ionize. And then our last one, calcium oxide, 0.1 molal. I value is going to be 2 because this is an ionic compound that will ionize. And when we multiply across, this becomes 0.2. Alright, so here's our table. We're just multiplying molality times I value to get our factor. So molality times I gives us the factor that we're looking for. And then we're going to rank these based on the factor. So we're going from lowest freezing point to highest. Since freezing points decrease, the more concentrated the solution, we're going to start with the factor that is the largest. That will drop the freezing point the most. So if we look at our values, obviously the KCl has the largest factor. So I'm going to call this one number 1. Then we go down our list. The next one is CaO, so this will be number 2. Then we have 3, 4, and 5. So this one is going to have the lowest. KCl will have the lowest freezing point because it has the greatest factor. And then this will have the highest. The NCl3 will have the highest freezing point because it has the smallest factor. Alright, so remember when we're trying to rank or get a relative idea of freezing or boiling point, we need to think about molality and the I value to get our factor. How big an effect do each of these components have on raising the boiling point or lowering the freezing point?